different measuring instruments. So first one we will discuss about galvanometer. Galvanometer.
Yes, sir.
This galvanometer is denoted by the symbol
G.
G.
Yes,
Okay,
sir.
it is an instrument used to detect small current. Okay,
Yes,
so
sir.
if you pass more current, it will work on the principle that if you pass more current, you will have more deflection. That is the principle on which it works.
Yes, sir.
I is directly proportional to
Theta.
theta. Current
Yes,
is
sir.
directly proportional to deflection. If more current is passed, then you will have more deflection.
Reflection. Yes, sir.
Then we discuss about one more point. It is called as a full scale deflection current.
Yes, sir.
The current, the amount of current required to pass such that the galvanometer will show complete reading is called
Yes, sir.
as full scale
Equal
deflection, and it
difflection.
is represented by Ig.
IG. Yes, sir.
Okay, then uh, now conversion of galvanometer, conversion of galvanometer, conversion of galvanometer,
Yes, sir.
conversion of galvanometer to into ammeter,
Yes, sir.
into ammeter. So we have to convert the galvanometer into
Ammeter.
ammeter. So now this is a galvanometer. To this galvanometer, current, some current is passing.
Yes,
So
sir.
what we discussed? What we have to do is to convert this galvanometer into ammeter. We have to connect a small resistance in parallel.
Yes, sir.
Small resistance in parallel to the galvanometer coil.
Yes,
This
sir.
we call it as shunt resistance.
Yes, sir.
Call it as shunt resistance. Okay. Okay.
Yes,
Now,
sir.
so here this current is I. So this is Ig.
IG.
So if the at the junction I current is flowing, Ig is flowing in this direction. So here current will be equal to I minus
IG.
Ig. Ig.
Yes, yes,
Now
sir.
here I can write the equivalent resistance of this combination is equivalent resistance of this combination is, as they are in parallel, Sg by S plus G
G.
is
Yes,
the
sir.
equivalent resistance.
Resistance. Yes, sir.
Okay. Now here the potential across this and this shunt and the galvanometer is same. So I will write Ig into G is equal to, as they are in parallel, the potential across them will be same. So
Same.
Ig
Yes.
into G is equal to I minus Ig
IG.
into S.
Yes, yes,
S
sir.
is shunt. So
Yes.
shunt is equal to Ig into G
I.
by
I minus
I
IG.
minus Ig.
IG. Yes, sir.
This is important formula.
Yes, sir.
This is called as shunt resistance.
Resistance.
Okay, this is conversion of galvanometer into
Ammeter.
ammeter.
Yes, sir.
Now, next one is conversion of conversion of conversion of galvanometer into voltmeter.
Yes, sir.
So now I have to convert this galvanometer into
Voltmeter.
volt voltmeter.
Yes, sir.
So to convert galvanometer into voltmeter, what we have to do? We have to take a galvanometer. We have to consider a galvanometer and then connect one high resistance in series.
Yes, sir.
High resistance in
Series.
series. Let us take this current as Ig.
Yes, sir.
So this is R. So the potential V is equal to Ohm's law is V is equal to Ig into G plus R.
Yes, sir.
Right. Now from here, what is the resistance? How much resistance we need to add? V by Ig
Hmm.
minus G is equal to
R.
R.
Yes, sir.
Okay, that's the resistance.
Yes,
That
sir.
is the resistance required.
Yes, sir.
Okay. Now, next one is Wheatstone Bridge. You know Wheatstone Bridge already we
Yes,
discussed, right?
yes, sir.
Wheatstone Bridge. Wheatstone Bridge is if you have a resistor like this. Now here one galvanometer
Yes, sir.
and this is P, this is
Q.
Q, this
R.
is R, and this is S. If P
P
by
by Q
Q
is equal to
is
R by S.
equal to R by S, then we say
Balanced.
bridge is balanced.
Yes, sir.
Then we say bridge is
Balanced.
balanced.
Yes,
Okay. Now, if the bridge is balanced, P by Q is then we can then that means here no current will flow. That means the potential here and the potential here are same. So
same.
if at all if there are any resistor or something, then we can write zero. Now we can see that if the bridge is balanced, this Ig will become
Zero.
zero.
Yes, sir.
Okay.
So,
Right. Now this is Wheatstone bridge. So same the application of Wheatstone bridge is meter bridge.
yes, sir.
Okay. Now we will discuss meter bridge. Application of Wheatstone bridge is meter bridge. Wheatstone bridge. In Wheatstone bridge, application of Wheatstone bridge. This application of Wheatstone bridge is nothing but meter bridge.
Yes, sir.
Meter
Meter bridge.
bridge. This meter bridge, we have a frame like this. Okay.
Yes, sir.
Now this is a wire from these 2 points. Let us calculate these as A and B. These are copper strips actually. Okay.
Yes, sir.
Now this is 1 meter. 1 meter is 1 meter 100 centimeters.
Yes, sir.
So that's why this is called as meter
Meter
bridge.
bridge.
And from the center we connect one galvanometer here.
Yes, sir.
Okay.
Yes, sir.
So let's see, galvanometer. Okay.
Yes, sir.
Now here we'll keep one resistance box, and here one wire or something. Okay.
Yes, sir.
So unknown resistance can be found. So now let us take that this resistance box. That means this is known resistance. This is unknown resistance. Let us call
Yes,
this as
sir.
P. This is Q. This
Q.
is R, and this is
Yes.
S. Now if
Yes.
the galvanometer shows 0, then bridge is
Balance.
balanced.
Yes, sir.
Then P by Q is equal to R by
R by S.
S. Then
Yes, sir.
this P is resistance, Q is resistance, R is rho L by
L
A.
by A. Yes, sir.
So if this length is L, as this is 100 meters, so this one will be
L.
100 minus
L.
L.
Yes, sir.
So by, so this is L. Other one is
100 minus
100
L.
minus L by A.
A. Yes,
This
sir.
rho is same, area of cross section is same. P by Q is equal to L by 100
100 minus
minus
L.
L.
Yes, sir.
So from this we can calculate the unknown resistance Q, because
Yes, sir.
P is known resistance. So that resistance of the wire we can calculate. This you know.
Yes,
Length
sir.
we will calculate from here because there is a scale here.
Yes, sir.
100 minus L will calculate, you substitute and you get Q value.
Q. Yes,
This
sir.
is this
Meter.
is meter bridge.
Yes, sir.
Okay.
Yes, sir.
Next one is this application of Wheatstone bridge. Okay. This
Yes,
meter
sir.
bridge. Now, next one is potentiometer.
Yes, sir.
Potentiometer.
Potential. Yes, sir.
Potentiometer.
Meter. Yes, sir.
Now, in this potentiometer, you have one battery and say a key,
Yes, sir.
then a variable resistance. Okay, or else this is called as rheostat.
Yes, sir.
Okay. Now, this we call it as primary circuit.
Yes, sir.
Primary circuit.
Okay.
For primary circuit, one cell will be there whose EMF is E and internal resistance is R, and that
Key.
is key K.
Yes, sir.
Now, one secondary circuit we will do. From here, we will attach one another cell connected to a galvanometer.
Yes, sir.
This galvanometer has got a jockey.
Yes, sir.
Okay, this jockey can slide on the potentiometer wire.
Yes, sir.
Okay, this potentiometer measures the or compares the EMF of the cell. Okay, it is
Yes.
used to measure the EMF of the cell
EMF. Yes, sir. EMF.
to internal resistance of the cell.
Yes, sir.
Internal
Resistance of the cell.
resistance
Of the cell.
of the cell. You can compare EMFs.
Yes, sir.
EMF of two cells. Okay,
Yes, sir.
that's the job. Okay, now, okay,
Yes,
so
sir.
ordinary voltmeter, what it does is it draws current through the circuit. Okay,
Yes,
so it
sir.
cannot measure the EMF accurately because it draws some current.
Yes,
Okay,
sir.
but this one does not draw. Potentiometer is based on no deflection method. Here the galvanometer shows zero reading. Okay, when they
Yes,
were equal. So it does not draw any current. Potentiometer does not any current, so it is more accurate. Why you
yes,
need
sir.
potentiometer? You can use voltmeter to measure the potential difference, na?
Yes, sir.
We use potentiometer to measure the potential difference because it is more accurate.
Of no current. Yes, sir.
Okay.
Yes,
Because
sir.
it does not draw any current.
Any
Normal
yes,
voltmeter draws current, whereas potentiometer
does
does
not draw
not
any
draw
current. Any current.
any current.
Yes, sir.
Okay.
Yes, sir.
Now, potential gradient. Potential gradient. Okay,
Okay.
it is the fall of potential per unit length. Let L be the length of the potentiometer wire.
Yes,
V is the potential difference. So V by L is the potential drop per unit length.
yes, sir.
Okay, so that is equal to volt per meter. Potential gradient is volt per meter.
Per
This is
meter.
called as potential
Potential gradient.
gradient.
Yes, sir.
Potential gradient is equal to volt per meter.
Per
Okay.
meter. Yes, sir.
Yeah, so now here I will just write here the different forms of it. Now V I can write it as now just V I will write it as I can write it as V is equal to
IR.
IR.
Yes, sir.
Now I can be written as E by total resistance.
Yes, sir.
Total resistance is R
Uh,
plus
internal resistance.
RH plus rheostat resistance plus internal resistance
Yes,
into
sir.
into
R. R.
R
Yes, sir.
to R. R is the resistance of the wire. Okay.
Yes, sir. Yes, sir.
So, okay. Now I can write here, okay, potential gradient K is equal to, so V is equal to like this also I can write.
Yes, sir.
So here I will write K is equal to V by L. V is equal to
I into R.
IR by
L.
L.
Yes, sir.
That is equal to, in another way I can write it as
E by
R into rho L by
by A.
A.
Yes, sir.
Rho L by A by L.
I L.
So this
L.
L and
Yes,
L
sir.
gets cancelled. Then I'll
I
get
into by A.
I rho by
By A.
A.
Yes, sir.
I can also write this as V by L, right? V by L means here V by L means here
I
IR by L. So this is R by L. Here I can write this as E by R plus RH plus
H plus R
small r
into
into
R by
R
L.
by L.
L. Yes, sir.
Okay.
Yes, sir.
So the potential gradient is directly proportional to R by L.
Yes, sir.
Okay.
Yes, sir.
And it is directly proportional to inversely proportional to
Area.
area
Yes, sir.
and
Directly proportional to current.
directly proportional to rho
Yes, sir.
specific resistance.
Yes, sir.
Okay, right. So I can write like that. Now,
Yes,
okay.
yes, sir.
Now what I'll do is V is equal to we can write here V is equal to KL.
KL. Yes, sir.
V is equal to KL from here. What is
Yes, sir.
K? K
Potential
is
gradient.
potential
Gradient.
gradient.
Yes, sir.
Okay.
Yes,
Now,
sir.
now what I'll do is, now I will keep the jockey here, lift it and place it here, lift it and place it here, till I get the galvanometer 0 as a galvanometer reading. I will keep on
Yes, sir.
placing the jockey at different positions. When
Yes,
I
sir.
get 0 in the galvanometer, I will measure the length as L.
Yes, sir.
Measure the length as L.
L. Yes, sir.
Now this one will become V is equal to K into
Into L.
L.
Yes, sir.
Okay.
Yes, sir.
Now here, uh, when you get a 0, that means when you are getting galvanometer reading as 0, that means here potential and this potential both are same. So
Same.
as
Yes.
the potential difference is same, that's why it is giving 0.
Yes, sir.
Okay. So
Yes, sir.
in this, this is the balanced condition. So I will write here, let us take this as E. Okay, this EMF, I will write it as italic.
Yes, sir.
So E is equal to X into L
Yes, sir.
or K into L.
Yes, sir.
Okay, because this potential are same. But
Same. Yes, sir.
you can substitute the value of K. K is equal to
V by
V by
L.
L. So we can write
Into
V by
V by
capital L
into
into
L.
L.
L. Yes, sir.
That is equal to
I
IR
R
by
by L
L
into L.
into L.
L. Yes, sir.
So I can write all the equations here. These equations, all you can write. I can substitute, and I can write I into rho by A
Yes, sir. Into
into
I.
L.
R. Yes, sir. Yes, sir.
Yeah, that is equal to E by R plus RH plus internal resistance R
Uh,
into
sir, rho
R
L by
by
A.
R by L into L.
Sir, rho L by A. LL gets
Cancel.
cancelled.
Right. Okay. So this many ways we can write.
Yes, sir.
Okay.
Yes, sir.
Now, if you want to write the uh, internal resistance, then we write like this: internal resistance. Internal resistance. Now, here, what we do? This is our cell.
Yes, sir.
Whose EMF is E, internal resistance is R.
R.
You have got a key, now,
Yes,
rheostat,
sir.
and yeah, this one. And in the secondary circuit, you got a cell EMF E
Yes,
and one external resistance. Let us call that as
sir.
R dash.
Yes,
You
sir.
just got a key here.
Yes, sir.
Okay, and then you have a
Galvanometer.
galvanometer connected to a jockey.
Job. Yes, sir.
Okay.
Yes, sir.
In the secondary circuit, this is secondary circuit and this is primary
Primary.
circuit.
Yes,
In
sir.
the secondary circuit, you keep that K dash open. You keep this
Yes,
K dash open. When K dash is open and you find out the
gal.
balance length, when you
Yes,
can
sir.
when you find out the balancing length. Let is E. So this
Yes.
we write E is equal to X into, let us note down that balancing length is
L1.
L1.
Yes, sir.
Now key is closed. Now key is closed. You
Yes,
close the
sir.
key.
Yes,
Now
sir.
close the key and now you find the balancing length. So now the balancing length is V is equal to, this is K,
Yes, sir.
potential gradient into
By
length
L.
is now L2. Okay.
Sir, V is
Now
equal to no, E is equal to.
V is equal to KL2.
Yes, sir.
So now we use the formula for internal resistance of the battery. So this is equation 1, equation 2.
Yes, sir.
Okay.
Yes, sir.
V is equal to E minus internal resistance. Na?
Yes, sir.
This is 2. The internal resistance R is equal to E by V minus 1 into R dash.
Yes, sir.
Okay, so R is equal to, now from 1 by 2 equation 1 by 2, what will get? E by V is equal to L1 by L2.
L1 by L2
L1
minus
by
1
L2 minus 1
into R dash.
into
R
R
dash.
dash.
Yes, sir.
So that is equal to, R is equal to L1
L1
minus L2
by
by L2
into R
into
dash. R
R
dash.
dash.
Yes, sir.
This is R.
Yes, sir.
R is the internal
And
resistance
resistance.
of the battery.
Yes, sir.
Okay.
Yes,
So
sir.
L1 minus L2
By
in
L2.
L1 minus L2 by L2 into
R
R
dash.
dash.
Yes, sir.
This is internal
Resistance.
resistance of
Yes, sir.
the primary
Primary circuit.
primary cell.
Yes, sir.
This internal resistance, this I am finding out.
Yes, sir.
So first I will keep this open. E is
E is
equal to
equal to K
KL1.
into L1
I close this
plus
one. V is equal to
K
KL2.
L
Then you have the formula R is equal to E by V minus 1 into R dash.
R dash.
R is equal to E by
Yes,
V is nothing but KK gets cancelled L1 by L2. So I substituted in place of E by V L1 by L2. Then I
minus
got R is equal to L1 minus L2 by L2 into
R
R
dash.
dash.
Yes, sir.
Okay.
Yes, sir.
Now you just see how to compare EMFs using this. Compare EMF. Now, how will you compare this one? See,
Yes,
so the basically you have one cell. EMF is E, internal resistance is R. It's got a key and a rheostat, and now this forms the primary circuit. In the
yes,
secondary circuit, you take one cell and you take another cell.
yes, sir.
Okay, then you take a galvanometer and connect it to a jockey.
Talking. Yes,
Let
sir.
us take this is E1 and
One,
this
two.
is E2.
Yes,
Okay, first you connect it to E1.
yes, sir.
Then E1 is equal to K into
L1.
balancing length is
L1.
L1.
Yes,
Then
sir.
you remove this connection and you connect it to E2.
E2.
Then E2 is equal to K.
L2.
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 Then E1
E
by E2 is equal to
L1 by L2.
L1 by L2.
L2. Yes, sir.
This is one way.
Yes, sir.
Okay.
Yes,
Now,
sir.
the other way you can do is you connect both of them in series.
Yes, sir.
First time you connect both of them in series. find out the balancing length. Then it will become E1
Yes.
plus E2
Two.
is equal to K into L1.
Yes, sir.
Okay. Then you connect opposite.
In parallel.
Series only.
Yes, sir.
You okay, you
Yes,
connect
sir.
oppositely.
Okay.
Oppositely, if you connect, then E1 minus E2
Okay.
is equal to K L2.
L2.
Then equation 1 by 2 will give us
E
E1 plus E2 by
E1 minus
E1
E2.
minus E2 is equal to
L1 by L2.
L1 by L2.
L2. Yes, sir.
Okay.
Yes,
So
sir.
this is how we use potentiometer. This is about
Compare here.
yeah to compare the EMFs.
Yes, sir.